So I'm delighted to welcome Maarten here today. So Maarten, until recently, had spent many years at the Max Planck Institute for Demographic Research, and he refers to himself as a health researcher and applied statistician. But recently, Maarten has moved to the University of Groningen and has a quite intriguing job title, which I'll have to read out: an assistant professor of precision drug therapy and real-world evidence. And I'm sure it'll be quite interesting to hear more about that specific element of your role, Maarten. But I know that we did ask you to come and talk more generally about the G formula method, and we know that you've published in this area, and a number of us are interested in hearing more about what it can do in demographic analyses, particularly in sort of complex life course analyses. So we're very pleased that you're here. So Maarten has got two master's degrees, one in demography from Groningen and one in applied statistics from University of Ghent. And then in 2016, you completed your PhD in pharmacoepidemiology, another word that is new to me. So that's very interesting. But your publication record is a real mixture of applied statistics, demography, epidemiology, all using, I would suggest, sort of sophisticated statistical methods. So publications ranging for methods to cope with age, period and cohort effects, using sibling models, papers looking at the implications of delayed parenting, papers looking at the effects of low income in childhood on later self-harm in adolescence, a whole range. So really fascinating. But without further ado, let me hand over this sort of stage to you. Generally, we'll take questions at the end, and I think Maarten's hoping to speak for about 40 minutes. So is there anything else I need to say? No? Okay, so thank you, Maarten.
All right, thank you very much for the introduction. That was a very comprehensive introduction. There was one thing missing from the introduction, which is that about 10 years ago, while I was doing my master's degree, I visited Southampton for 1 month. At the time, I was hosted by Sabu Padmadas and Andrew Hind. It was a very nice time. I quite liked it. So it's very nice that that I can also now present here instead of being a student as a professor. Well, as someone who's giving a short talk.
So it's welcoming back, really, rather than
yes,
welcoming you.
That's right. Yes. Yeah. What else can I say? I could speak about pharmacoepidemiology and precision drug therapy, but I guess I should start talking about the actual talk, the G formula. And what I can say, which is about both the talk and my new title, is that the G formula is a method that was developed to model dynamic treatment regimes originally. So if a patient gets a drug based on their covariate background, then of course they respond to that drug in a certain way. And then based on the response, the treatment might be altered and so forth. And the life course is a little bit like that, because if you enter school, usually not based on your covariate background, although there might be some things related to covariate there already. And then depending on how you respond to school, I don't know how the UK system is, but if you do really well, you can go to a different type of school than if you don't do so well. So the life course also is a little bit dynamic. And that's why we started using this method also in demography. And now the plan is actually to bring it back and go back to the pharmacy world and to look at these dynamic treatment regimes in the setting that it was originally developed for. I'm going to share my slides. Let's see here, or share my screen. Let's see here. So full screen. All right, so you should be able to see my screen. As Anne already said, I guess most of the questions are at the end, but if something is unclear, you can also just ask a quick clarification question. I'm fairly robust to interruptions. So I don't have to introduce myself. That was already done. Very nice introduction. I should maybe quickly introduce Ben Wilson, because the paper was written together with Ben. I think many of you probably know him because he is a UK national, but he lives in Stockholm. He works at the Stockholm Demography Unit. Recently got a big ERC grant, so he's leading a team now And he also has an affiliation, I believe, still with the methodology department of the London School of Economics. When we worked on this, I was mostly doing the methods and Ben was doing the fertility part. So I'm slightly, whenever I give this talk, I'll slightly dread the sort of sociological fertility questions because please still ask them, that's fine. But he should be the one to answer those, I think. But Ben is also a methodologist, so he actually also knows quite a bit about the G formula. The paper has been published in the Journal of the Royal Statistical Society last year, and has the same title as the talk. And the basic sort of premise, if you will, is that socioeconomic determinants and fertility are all interrelated, and so they're there's complex relationships. We can imagine that education affects employment and partnership, but partnership can also affect employment. These things all can affect each other, and they're also all interrelated with fertility. So you can sort of imagine that everything affects potentially everything. And what we normally like to do in science, I think, is we try to avoid complexity and sort of isolate the effect of a single determinant on the outcome of interest. And one way of doing that is I think maybe the preferred way of doing that is the conditioning on unobservables approach. Think of natural experiments and the methods that exploit them. You could think of difference in differences designs, or regression discontinuity, instrumental variables. If you can apply those and the so-called exogeneity assumption holds, which I won't go into here, then these methods have a strong internal validity. So you can really make strong causal claims. I like to use these methods as well, although I haven't had much of a chance. It's more applied in sort of econometrics and economics, although some demographers do as well. But they do have some issues with them, namely generalizability and mediation. Firstly, generalizability. Let's say that we're interested in the effect of education on fertility, and we want to exploit a natural experiment. Then one thing we could do is we could look at mandatory school leaving age. So people have to stay in school until age 14, and then some government decides, and this has happened in various countries, that the mandatory school leaving age should increase to say 16. Then that's an exogenous influence. You're now forced to stay in school until age 16. So we could compare the cohort of people who finished school just before this new policy was put in place, and the cohort of people who was experiencing the new regime. So they had to stay in school until age 16. You could compare the fertility of these two groups maybe 20 years later, after they've gone through their fertile career. And the difference might be the causal effect of education. Now that could work. We'd have to examine it a little bit further. That could work, but it is not super generalizable. The only people who are affected by this intervention are those people who would have left school at age 14 and now have to stay in school until age 16. That's a particular group of people. Maybe they have a lower socioeconomic status, or there's some other reason why they would leave school early. People who would have stayed in school until 16 or 18 anyway, or 20, they're not affected by this policy. So it's not very generalizable. The second issue is that you can't really do mediation analysis generally with these type of natural experiments, and I will show that here. So we'll have a little bit of counterfactual notation, but not very much. So here we have fertility Y, and then here is, we sort of say do X. So let's say fertility Y when we set the fertility regime, the education regime to the age 14 mandatory school leaving age regime. And this would be fertility Y when we set it to the age 16 regime. So it could be the cohort just before and the cohort just after the implementation of the policy. And the difference would be the causal effect. But when we do mediation, we want to know not just the effect of X on Y, but also what part goes through M, so the mediator. In this case, that could be employment. Now, when we want to isolate the effect of M, we need a little bit, we need some more quantities, at least one more quantity. So let's see what we need. Here we have whether the mediator is affected by the exposure, in this case education, and whether the exposure is actually before the intervention or after intervention, so age 14 regime, age 16 regime. So this would be fertility when we are in the age 16 regime, and the mediator M has taken on the distribution that it has under the age 14 regime. So this thing is the same as the YX, it's just with expanded notation. And over here in the bottom right, the green ones, we have the age 16 regime, and of course the mediators take on the distribution that they would have under age 16. But you'll notice that X and MX and X star, MX star are, of course, they're coupled. When X changes, MX also changes. And when X star becomes X star, M becomes MX star. So we can't isolate the M part from the X part. So we need one of these two quantities as well. Fertility, when we're in the age 14 regime, but the mediator distribution is as if we're in the age 16 regime. And the fun thing about thinking with counterfactuals is it makes things a lot clearer. I can certainly imagine this situation, but it also makes it clear that this is a little bit artificial, and mediation, strictly speaking, is a bit artificial. Because could you imagine a population in which people spent up to until age 14 in school, then left, but their mediator distribution is as if they had spent 16 years in school? That's sort of counterfactually very difficult to imagine. You could maybe have a data set where people lied on their resume. They said they spent 14 years in school, but they said they spent 16 years in school. But of course, education is much more than just what you put on your resume. It changes how you think. It changes your network. So even if you had that data set, you wouldn't have really the proper MX star distribution. We could also use YX star MX, so the age 16 regime, but people have the mediator distribution, employment distribution, say, of people who spent 14 years in education. But also that is kind of strange. So in a natural experiment, you don't really observe those two quantities, and so you have to construct them under certain assumptions. And that's where the conditioning on observables approach comes in. And the G formula is sort of the, I guess, the premier method in that framework. So the idea with the G formula is that we're actually going to try and model complexity. It's embedded in the potential outcomes framework, which the conditioning on unobservables approaches, the natural experiment, so to speak, are also embedded in. So it's not fundamentally different, though in practice, of course, it's quite a different approach. With the G formula, we can model time-varying confounding and intermediate confounding. I think most of you will be familiar with time-varying confounding. Intermediate confounding is where the mediator of interest is also a confounder. This creates a bit of a problem because we want to adjust for a mediator to get rid of the biasing influence. When you adjust for a mediator, you also lose the effect via the mediator, so you block a confounder and you get rid of the effect via that particular mediator. With the G formula, we can actually adjust for the confounder while still allowing an effect via that mediator. You'll see soon how that works. So in short, we can try and model hypothetical changes in life course processes while accounting for their interdependence. So in the paper, we have a number of research questions, but in this talk, I will just talk about these two because that is about 40 minutes. So we're going to ask, what is the effect of education on birth risks over the life course? And to what extent is an effect, if we measure one, and of course we are going to measure one, to what extent is this effect mediated by work and partnership? We're going to use data from the 1970 British birth cohort study. It has about, I think it's about 16,000 N, so people measured. About 8,000 of those are women. And then of those 8,000 women, about 4,000 had missing data on some of the baseline covariates. So we ended up with 4,000. And of the remaining 4,000, about 800 had missing information on some of the waves. Now, I'm personally actually quite a fan of imputation techniques, especially multiple imputation. And you'll also notice, for those of you who are familiar with multiple imputation, that the G formula in its implementation is quite similar to multiple imputation. Very, very similar approaches. So it's actually very easy to unify these two things, to combine them. And in some of my papers I do. So if you're curious how to do that, you could check some of my other papers. In this paper, we didn't do it for two reasons. The first reason why we didn't impute is that the paper is meant sort of as a tutorial for demographers and also other social scientists to see how you could apply the G formula and why you might want to do that. And so we didn't want to make it more complex by also adding an imputation layer to the estimation. That's the primary reason. The secondary reason is that if we look at the baseline variable distribution of women who had complete cases versus women who had missing waves, those distributions were similar enough that we knew, or at least we strongly believe, that imputation would not have had an effect on the results, but only on the precision of the estimation. So in this data set, we have time varying measures up until age 38. So we go from 16 to 38. We have fertility, which is, do you have a live birth, yes or no? If you have a live birth, is it a singleton, a twin, a triplet, and so forth? And also, how many children do you have up until this point in time? So sort of counter of children. Employment is, are you employed, yes or no, at each age? Is it a part-time job or a full-time job? And is it a blue-collar job or a white-collar job? And then there's education, which is simply, are you in education, yes or no? And what duration have you spent in education? We would have liked more information, so also on say, what type of degrees. There is some information on degrees in the BCS 70, but we didn't find it very high quality, so we decided not to use it. And then there's partnership status, which is, are you single, cohabiting, or married? In terms of baseline characteristics, we have the father social class, the respondent's mother's age at birth, the respondent's number of siblings. These two are because we didn't have information on ideal family size, or what do people want in terms of numbers of children, or the timing of birth. And there are some papers that say that people who come from large families would like larger families themselves, more likely, and people who come from small families would prefer smaller families themselves. So we try and capture a little bit of that information. And then there's region. So are you from London? Are you from the southeast or the southwest, or the Midlands, and so forth? And age. Now, age is not, of course, a baseline characteristic, but it changes in a deterministic fashion. So we don't have to model age. We know exactly what age you are. So then we assumed a certain causal structure. Of course, there's many possible causal structures you could assume. We're assuming the following one, which is a single year cross-lagged structure. Basically, we're saying that the variables at time point t, so fertility, education, work, and partnership, that's here, say 17, but it could also be some other time, at time point t are allowed to be a function of the variables at time point t minus 1, so the previous year, plus the baseline variables, which are allowed to affect everything. There's a lot to say about this. Often I get asked about arrows, like why did you draw this arrow or some other arrow? The real question should actually be which arrows I didn't draw and why I didn't draw them. If you see an arrow, that means I'm allowing this relationship to exist in my modeling procedure, but the model could, of course, estimate, so this arrow, for example, from fertility at 16 to education at 17, that could be a coefficient or even a set of coefficients. The model could set that to 0, meaning that there is actually no arrow, but I allow it to be estimated. When I don't draw an arrow, of course, I don't allow the estimation, so I'm imposing something, which is a much stronger thing to do. You'll notice a number of arrows that are missing. So firstly, you see that there aren't any arrows at time point t to other variables at t. So nothing from 17 to other variables at 17. The main reason why I do this is because at the time we found it to be a bit problematic. If you have chronological ordering, you know that something happens before something else, and you have some informational causal ordering. The cause has to precede the effect. But with time points at 17 or at 18, we don't know what came first. Did your fertility happen before your education change, or your work change happened before your partnership change? So all possible errors, there could be all kinds of errors, all kinds of directions. We chose not to do anything with that. What you sometimes see in present day papers, but I haven't seen a good study on this yet, and if this is a good choice, is that they randomize the order for each bootstrap iteration, so that you allow all kinds of directions and you get some sort of average out of it. I'd like to see a proper methodological study on that. What you also don't notice is arrows from, say, 16 to 18, or from 17 to 25, or something beyond 1 year. That is something I've tried in various papers from multiple lags, lag 1, lag 2, lag 3, lag 4. I've always found that it has no effect on the ultimate estimation. So we estimate population average effects, and it does almost nothing. Conditional on the variables of 1 year ago, the variables 2 years ago, 3 years ago, 4 years ago have almost no effect, which I think also fits closely with the so-called Markov assumption. What you see here is actually the same as what you just saw in the previous slide. So, for example, we're going to fit a model for fertility as a function of fertility, education, work, and partnership, and the baseline variables in the previous year. So fertility is a function of some intercept, age terms, baseline variables, mediators M, and some interaction terms L, interactions between time-varying covariates and between time-varying covariates and baseline variables, and with age also. But we don't just do this for fertility, we also fit a model for education, for work, and for partnership. So we're fitting multiple models together. So Y is whatever outcome variable we're interested in, and G is the appropriate link function. Is it logit, or is it, are we fitting a categorical model, multinomial model, or so? So we're fitting these models, and after we fit the models, what we do is we don't look at the coefficients, or maybe we look at them, but we don't immediately use them. We are going to use them instead in a scenario simulation. And the first simulation is the so-called natural course, which is a reproduction of the empirical data. So we take observed values at age 16, and we put those in the model we've just estimated. So the A's go here, the B's go here, the M's go here, the L's go here. And we've estimated these coefficients. We did that in the previous step. So we have an eta, we have an alpha, a beta, a mu, a lambda. And that means I just have numbers here now. I can add them all together. I apply the inverse link function of G, and then I get some estimated, say, probability that someone has a birth at 17 as a function of the previous year's covariates and the baseline variables. So if, let's say, this woman has a 20% chance of having a child, I don't actually just use that 20% here. I instead put that 20% as a parameter in a binomial distribution, and I draw from that. So this woman had a 20% chance of getting a 1 and an 80% chance of getting a 0. So I do that, and I give her a 1 or a 0. Then I do it with education as well, with work and with partnerships, so that I have my simulated data here. Once I have the simulated data, I can put those in my model again, do the same trick again, and then I have sort of simulated values at 18, then we go to 19, then we go to 20, all the way up until 38. And of course, if someone has a birth, there's also a probability that she has a twin, for example, or a triplet, and so forth. So also sort of deterministic variables get updated, including age. Now I don't do that once. I do that many times, because if someone has a 20% probability, then over multiple iterations, we would like to see her have 2 babies or say 20 babies over roughly 100 iterations. So on average, she does actually have this 20%. And then we average over multiple Monte Carlo iterations to stabilize this process. Now, this procedure should produce simulations that look like the empirical data because we use starting values at age 16 and we estimated our models to the empirical data as well. But we should check that because these could be highly nonlinear models. In this case, they're not super nonlinear, but they could be. And of course, they all interact with each other. They feed into each other. So one thing to do is to check if it actually matches. So here we have the proportion of women by parity at age 38, the natural course versus the empirical data. Here's the parities. And then you see it. Parity 0 at age 38 is slightly underpredicted. We've got 22% here. It should be 24. 31 is predicted quite well. 32 slightly overpredicted, and so forth. Overall, we were quite happy with this. And the fun thing about this paper is that this paper was under review the longest of all of my papers. I did most of the work on this paper in 2016. Back then, I was quite good at the G formula, not as good as I'm now, I would like to think. I think I could have done better if I do it now. But at the time, we were quite happy, and I was fitting these models more or less by hand. There are procedures now to do this with sort of machine learning approaches as well to get even better fits. Now, you should not just check one aspect. We should not just check fertility. Maybe, for example, we're mispredicting parity, not because the model for fertility is wrong, but because my model for work is wrong, and that feeds into the fertility model. So you have to check all of these variables, and also not just parity. You might also want to check numbers of births over time, so many dimensions. And here comes a question to you, not a question you have to answer right now, mind you, but that is a genuine question. So one thing I'm very interested in is these G methods, and we're modeling with the G formula, we're modeling the joint distribution in the data. Here we're just looking at one aspect of the data, but we really should be looking at it jointly. So not just parity, but also parity by employment, by age, by all these other dimensions together. But it's notoriously difficult to visualize more than 3 dimensions in tables and in graphs. And there's very few, I've seen very few papers that really look at this. I know people have looked at it. At one point I had the chance to talk to the dean of my new faculty, who happens to be a physicist and who tried to do this apparently as well, not with the G formula, but with some other approach. He said he failed at it also. But nevertheless, if someone knows a good way of checking joint distribution compared to the actual data, the model of the joint distribution versus the data, in a comprehensible way, I would really love to know it, because it could be super helpful for G methods in general. So please send me an email or let me know after the talk. So if we're happy with our fit, we then go to a second scenario, which is the intervention scenario. We do essentially the same thing as previous, but now we're going to intervene. In this case, we're going to intervene hypothetically on education. In this case, we don't allow 50% of women to leave higher education. The basic idea was that we wanted to reproduce a societal trend, which is that more and more women enter higher education, and we wanted to reproduce this. So here, if a woman who belongs to this sort of chosen 50% had a 0 simulated, we don't allow that, we make that a 1. And also at 18, also at 19, up until age 23. And of course, if I change these covariate values, then everything else will also change, because work and partnership and fertility and also future education are a function of these covariates. So if work changes, maybe then your fertility changes, or work changes, which then changes your partnership, which then changes fertility. And there is also direct effects that are possible. Now there's many possible interventions you could do. And I think this is one of the fun things about the G formula. If you just have a model, a regression model, and you have a coefficient, we're inclined to just interpret the odds ratio, and that's it, our job is done. But when you simulate scenarios like this, you could imagine all kinds of interventions you could be doing. hypothetically. But you do have to make clear what your intervention is. So here, the intervention size, not the effect size, but the intervention size itself can be visualized. Here we have the percentage of women in education, goes from 0 to 100. Here we have age, it goes from 16 to 38. And this was the observed distribution at the time. And then this is the counterfactual one. So effectively, we're comparing the scenario where we have education as distributed according to the blue area versus the scenario where it's both blue and green together. And then this is the effect. Well, not yet the effect, but this I'm going to show you the effect. So here we have the number of babies born, goes from 0 to 5,000 to these 3,200 women. Age, again, goes from 16 to 38. And then the natural course is this one. You can sort of still see it's kind of model-based. It's a little bit too smooth. And then there's this little thingy here. But it looked enough like the empirical data. And then this is the difference when we sort of keep women in higher education until age 23. So that's 4,500 babies. That's 500 babies fewer, which is 10% less. That's the effect. And this is the ratio of those two curves. So of course it starts at 1, then there's sort of a delay in childbearing, and there's a catch-up in the end. So we see both tempo and quantum effects. We did not explicitly model those, which was interesting, that we still see something like that. The quantum effect, of course, is, well, it's 10% less at the end. So that's the catch-up is not complete. There are additional waves of what is it, BCS 70 these days. So we could actually continue this maybe in a future paper. I don't think I will do it, but people could do it if they wanted to. So that's the effect. Then we want to know mediation. How is this effect mediated by work and partnership? So we have to create a third scenario that sort of corresponds to the X star MX. This is actually easy almost, because we have to do less simulation. What we do is we'll take values, we draw values from our intervention scenario. So we already, of course, created the intervention scenario, so we just draw from that by age. And we draw the work and partnership values from the mediator, as from the natural course scenario. So the education values are as if intervened on, and the work values are, and partnership values are as if not intervened on, natural course. And then all we have to do is simulate fertility. And then, of course, you take the difference between the mediation scenario and the natural course to get the mediated effect. So here we have the percentage of the total effect. It goes from 0 to 100. Of course, the axes go from -60 to 150, but actual effects don't go outside those bounds. They could, it would be fine. Here they don't. So in the beginning, we see a strong direct effect. So simply being in higher education, or being in education, I should say, not higher education, prevents childbearing to a certain extent. Then after they're allowed to leave school, we see that the mediated part increases. So in the long run, being more highly educated changes your partnership trajectories and changes your employment trajectories, and those go on to change your fertility sort of in the long run. Now, of course, all of this relies on the assumption of no unmeasured confounding. The advantage of these conditioning on unobservables approaches, the econometric approaches, is that we can try and avoid that if our exogeneity assumption holds. But here, we don't have that ability. So we have to rely on everything that's measured. And it might be that we haven't measured everything. In fact, we probably haven't. That's generally the case. So what if there is a confounder C that affects both education and fertility that we haven't measured? We could think of all kinds of possible confounders. In this paper, we were thinking of something like traditional values. We didn't really have very good measures for desired family size or desired educational outcomes. So we were thinking of traditional values. So maybe some women come from families that say, well, women shouldn't have a very high education, they should be in the household, and they should have a big family. So sort of a negative force on education and a positive force on fertility. Well, we haven't measured this, so what can we do? Well, one of the One of the contributions of the paper is that we also show how to do this with the G formula. There are other papers that show how to do this in general. Then I figured out how can we do this for a G formula. And the trick is quite simple. A confounder, of course, is a variable that affects both the exposure and the outcome. But statistical models don't know the direction of causality. They're always just models of association. So instead, we can create the confounder as a function of x and y. So we allow x to affect c and y to affect c. Strictly speaking, in causal speak, you're creating a so-called collider. But of course, models cannot distinguish between colliders and confounders. So if I create an effect of x on c that is very strong, then in turn c will have a strong effect, in air quotes, on x. So I ended up creating one that has an effect of 2.3 of not being in education, and an effect of 2.9 on birth at each time point. These are odds ratios, by the way. So these are quite strong confounders, I would say. And then we adjusted for this artificial confounder. And then this is what we see. So here we have the ratio of number of children ever born. The gray line is the one you observed previously. The black line, which actually also should have started at 1, that's a little bit of an error here, but you see overall the shape remains the same. The effect goes back to 1 in the end. The quantum effect disappears, the tempo effect remains. So why does that happen? Well, the effect goes away specifically because I was looking for how strong does a confounder need to be to make the effect go away. This is sort of the same logic as the E-values approach that Tyler Vanderweel, perhaps you might know of him, likes to use. Then the question is this a realistic confounder? So what we did is we looked at our models and we looked at the strongest variable, the variable with the strongest effect on fertility. And in our model, that was marriage. I think in general, marriage is a fairly strong force, especially in older cohorts, on fertility, but it had an effect of 2.1. So in short, this confounder would have to be stronger than one of the strongest variables on birth. And that we thought was perhaps a little bit unrealistic. In other words, we're saying that probably such a confounder should have a less strong effect than 2.9, meaning that the true effect is somewhere between the black line and the gray line, and hopefully closer to the gray line than to the black line. In short, there should be an effect of educational fertility. We don't know exactly how strong it is. We hope it's closer to gray than to black. That is sort of most of the talk. I'll say one more thing. So that's most of the talk. Now I do like transparency where possible. I work with a lot of Scandinavian data, which unfortunately is not so easy to share. But here we're working with the BCS, and the BCS is open to anyone who works at a public institution. You just have to sign up to the UK Data Archive, which is great. It's good that you guys do that. And with you guys, I guess I just sort of generalized to people in Britain. Here's the code is also there. You can find it actually also on the website of the JRSS, but they make you sort of solve a puzzle to get it. So I also have it on my GitHub. It's easier to find there. I've had 4 or 5 people ask me for the code before putting it on GitHub, or they ask me without knowing it's on GitHub. I always ask them to send me an email to make sure, to tell me if they were able to reproduce the results. I've not gotten any emails back. This could be good news, it could also be bad news. It could be good news that they were able to do it and they forgot to send me an email, or they couldn't do it and they're embarrassed to ask for more directions. If you're gonna try and you can't do it, also please let me know and I will try and help you reproduce it if possible. But it should be reproducible. Okay, so the conclusion, if we keep about 50% of women in higher education up until age 23, and we found a 10% reduction in fertility. First, there's a strong direct effect, so simply being in higher education, or just in education really, prevents childbearing to a certain extent. In the long run, a different education trajectory changes the partnership trajectory, changes the work trajectory, and those go on to affect fertility in the long run. And we claim that this is all robust to confounding. Thank you for your attention.
Thank you very much indeed, Maarten, for taking us through some quite complex concepts and statistics there in a very simple way. Thank you.